Hello and welcome back. What we're going to be taking a look at today is how we can use what we know about radical functions, so square roots and functions, and use that to help us with graphing horizontal parabolas and circles and other non-functions potentially. Besides being a good exercise in how we can use radical functions, this also is actually very practical because a lot of the technology that we tend to use in schools, such as a TI-83 or 84 graphing calculator, doesn't really have a easily manipulable way of working with non-functions. So this is going to give us some options to graph things that normally we would have some difficulty with. So first things first, it's worthwhile to note what it is about something like, say, a vertically oriented parabola that we actually like. So very first thing, it is a function. It passes the vertical line test. So this is very easy for most graphing calculators to deal with, and so it's pretty much a simple scenario. It is worth noting that our vertex form, it would be written as y equals some number times x minus the x coordinate h of our vertex squared plus k, the y coordinate squared. This is what we would call the hk or vertex form. And again, this can be graphed very easily into most systems that we would be using in classes. And it also has an axis of symmetry at x equals h. Now, compare that to a horizontally opened or oriented parabola, and we would have something maybe like this example, which very clearly fails the vertical line test. You can see those three dots, one of which is what we would call the focus, which we'll learn about later, but the other two of which are vertically aligned at what looks like the value of 1, 2, 3, 4, 5. And so you have two different points that share the x value of 5. If you have the same x value having two different y values that pair with it, it is not a function. In the vertex form, you would have a very similar format, but instead of x minus h squared, you have y minus k squared times a plus your h value. So slight rewrite, but the same general premise. The k value is always attached to the y, the h value is always attached to the x, but since it opens to the sideways we have direction, we have y squared. And this cannot be entered into standard graphing calculators as is, but we can rewrite it. Okay, and the way we're going to write it is by taking advantage of this function's axis of symmetry, namely y equals k. So by taking advantage of y equals k, we can actually just cut it straight in half, and you'll notice that everything above that will actually be a function, and everything below that will also be a function. So we're going to literally split this down the axis of symmetry into two functions by doing something surprisingly simple. We're going to solve for y. So to rewrite as multiple functions, all we have to do is solve for y. In the process of doing so, we're going to start with our function. Let's just use the function from the previous slide. Excuse me, I keep saying function. Equation. These are not functions, aren't they? So x equals 1/2 times y minus 1 squared plus 3. You're going to subtract 3 from both sides. Then you're going to multiply by 2 to remove that 1/2 in front of the y minus 1 squared. And that's going to give you, you can either write this as 2 times x minus 3, so x minus 3 in parentheses, or you can write it as 2x minus 6. I've chosen to expand it here. That's up to you. And then you have y minus 1 squared on the right. You then are going to square root both sides to get rid of the square above y minus 1 squared. And it's worth noting that if you ever have to take a square root of a square, what you have left inside is always an absolute value. And whenever you have an absolute value, what you're really saying is there are two versions of what's inside that absolute value. The one that is equal to a positive number, and the version that's equal to a negative number. But remember, the absolute value makes them both positive, so in the end it doesn't matter. But we're trying to solve for all the possibility of x, so we have to account for this. So because of this, you actually end up converting the absolute value on one side into a plus or minus on the other, because what's inside y minus 1 could have either been the positive version of this square root, or it could be the negative version, and when you take the absolute value, it always gives you the positive. Well, because we have plus or minus, we would normally split this off and write it as two functions. I'm going to save a little space and use plus or minus. Do keep in mind that for me at least, I always want to see a plus written separately from the minus. So when I add 1 to both sides, I would have y equals 1 plus the square root of 2x minus 6, and a second equation of 1 minus the square root of 2x minus 6. Now if I graph them together in Desmos, you get something that looks actually rather nice. The red upper curve is our 1 plus the square root, the blue lower curve is 1 minus our square root, and each of these on their own, if you just cover up one color or the other, is actually going to be a function. Together, they end up making a full-on sideways opening parabola. In fact, this matches pretty nicely the graph we had before. The dimensions and the spacing is a little different, but this is a parabola that opens to the right with a vertex at 3, 1. And so this is how we can break it up. If we want to try the same thing with a circle, let's just quickly come up with a circle. Let's just try, I don't know, x minus 1 squared plus y plus 3 squared equals 4. So you may know from what you've seen in geometry that this would have a center at 1 comma negative 3 with a radius of the square root of 4, which would be 2. So how would we solve this? You do the exact same thing. You solve for y. So we want to get everything that's not a y term or trapped currently with a y term to the other side. So let's start by subtracting that x minus 1 squared. Just the whole thing. We don't need to expand it. Frankly, let's just not expand it. It's actually easier to read if we don't. And then again, we have to take care of that square on top of the y plus 3, so let's square both sides. And once again, please remember, square root of a square is an absolute value. That absolute value is often written as plus or minus the square root. Most of the time when you've seen this in the past, it's very possible that you completely skipped the absolute value part. And if you continue to do that, that's okay, but just keep in mind what it is you're actually doing. And then again, you're just left with, well, let's subtract 3 from both sides. And you're left with two functions once again, y equals negative 3 plus the square root, and y equals negative 3 minus the square root. And so when you do this, once again, you have an upper curve, which is a function, a lower curve, which is a function, and you end up having a circle with a center of 1, negative 3, and a radius of, oh, that's a typo on my part. I'll have to go back in and fix that, but a radius of 2, the square root of 4, it should say. Hopefully this has helped understand how we can convert certain non-functions into pieces that are each functions to help us with graphing, and have a nice day.